Sampling distribution of Pearson's R. Like all statistics, Pearson's R has a sampling distribution. Different samples will result in different values of Pearson's R. Assume that the correlation between quantitative and verbal SAT scores in a given population is 0.6. In other words, rho is 0.6. If 12 students were sampled randomly, the sample correlation R would not be exactly equal to 0.6. Naturally, different samples of 12 students would yield different values of R. The distribution of values of R are after repeated samples of 12 students is the sampling distribution of R. This figure shows the sampling distribution of R when rho, the population correlation, is 0.6 for a sample size of 12. You can see that the distribution has a negative skew. The upper tail of the distribution is limited by 1 since correlations can never be larger than 1. However, the lower tail extends quite a long way. With such a small sample size, sample correlations below 0 are not rare. The larger the population correlation rho, the larger the skew. This graph shows the sampling distribution for rho, which is equal to 0.9. When rho is negative, the distribution has a positive skew. This graph shows the distribution for rho equals negative 0.9. Referring back to the SAT example, for which rho equals 0.6, suppose you wanted to know the probability that in a sample of 19 students, the sample value of R would be 0.75 or higher. You might think that all you would need to know to compute this probability is the mean and the standard error of the sampling distribution of R. However, since the sampling distribution is not normal, you would still not be able to solve the problem. Fortunately, the statistician Ronald Fisher developed a way to transform R to a variable that is normally distributed with a known standard error. The variable is called z prime, and the formula for the transformation is shown here. The symbol ln stands for natural logarithm. The details of this transformation are not important for present purposes. The critical thing is that this transformation produces a variable that is normally distributed. In order to do any calculations using the sampling distribution of z prime, you need to know its standard deviation. The standard deviation of this distribution, also called the standard error of z prime, is equal to 1 over the square root of n minus 3, where n is the number of pairs of scores. Let's return to the question of determining the probability of getting a sample correlation of 0.75 or above in a sample of 12 from a population with a correlation of 0.6. The first step is to convert both 0.6 and 0.75 to z primes. This can be done from the formula shown previously, a table, or an online calculator. The values are 0.693 and 0.973, respectively. The standard error of z prime for n equals 12 is 0.333. Using the values just calculated, the problem is pretty easy. We have a normal distribution with a mean of 0.693 and a standard deviation of 0.333. We just have to figure out the probability of obtaining a value of 0.973 or higher. The answer can be found directly from the normal calculator. As you can see it is 0.2.